Hello everyone, and welcome to today's lecture on vector-valued functions of a scalar variable. Specifically, these deal with functions from some domain set that's a subset of the real number line into some range set, which is a subset of n-dimensional space, where specifically we can write that the position vector, we'll call it r, is really equal to this function evaluated at some t value, where t is an element of the domain set. So really what this is saying is that r, the position vector, is a function of some parameter t. We call t the parameter of a given parametric curve, and this is exactly what r of t is. R of t is a parametric curve. Or some curve in n-dimensional space. In most of the examples that we'll talk about will be in 3D space, but this concept can be applied in any number of dimensional spaces. So really, we want kind of a nice way of writing down exactly what this parametric curve looks like. The vector of equation of the curve looks like this, but if we want to write this down in, say, a Cartesian coordinate system, then the vector equation of the curve can be written as follows in Cartesian coordinates. And specifically we'll stick with 3D. R of t is equal to a vector of three single variable functions, x of t, y of t, and z of t. Where a slightly easier way, this is one really nice way of writing this down, but a different way of writing this down would be to write it as, well, if you remember basic vector addition and subtraction, this is the same thing as saying x of t multiplied by the vector 1, 0, 0 plus y of t multiplied by the vector 0, 1, 0 plus z of t multiplied by the vector 0, 0, 1, which are just the unit vectors pointing in the individual Cartesian coordinate directions. Typically, notation-wise, we can call this vector I hat. We can call this vector j hat. We can call this vector k hat. So another equivalent notation for r of t for any vector parametric curve or scalar function, or a vector valued function that's valued in three-dimensional space, would be x of t times I hat plus y of t times j hat plus z of t times k hat. And you'll notice here, to denote a vector, I use the above arrow symbol. You can use underline to denote a vector. You could also use the above arrow symbol. The book that we use uses a bold for vectors, which is another common notation, but it's important that you see this. And I'll try and stick to just using underline for vector so that I'm a bit more consistent, but I might occasionally use the over arrow notation for vector as well, in which case you shouldn't be worried at all. So we have two very convenient representations of this vector function in Cartesian coordinates. And now I just want to draw kind of a picture of what exactly this is giving us. Now remember I said that we can apply the vector concept in any number of dimensions, and it's very useful in higher dimensions. However, this picture will just be in 3 dimensions, where we'll say that this is the x-axis, this is the y-axis, and this is the z-axis. And therefore, our unit vectors I hat, j hat, and k hat look like this. This is a 3-dimensional axis and a 3-dimensional picture. Now, roughly speaking, what this this is giving us, if you have a given vector valued function of a scalar variable or a given parametric curve, is you have essentially some curve that at every given point or every given value of the parameter, a point of that curve is mapped to. So for example, this point right here, this vector right here, would be r evaluated at t1. As t increases, t2 is a little larger value than t1. You could say have another position vector right here, r at t2. But in general, for points on this this parametric curve, for a given value of t, when we plug that value of t into the function, the parametric curve function, we get back out a position vector of points on this curve. So we'll start with a relatively basic example and then move on to some more complicated examples a little bit later on in the lecture. And for this first example, we'll say, let's consider the position vector, or the function, vector valued function of a scalar variable r times cosine of omega t, r times sine of omega t, and then we'll say lastly k times t. For t, start with t at 0, and then allow t to be any positive real number. So want you to think for a little bit about exactly what this is going to look like. But sure enough, at t equals 0, say, the z coordinate is 0, the x coordinate is going to be r times cosine of 0, which is r times 1, and r times sine of 0, which is 0. So the y coordinate is 0, the x coordinate is given by r at this point, and the z coordinate is 0. It's exactly this point right here. Then if we go to the value, another value of t, we'll say when t, and I guess we should make a table here to kind of get a good idea of what this is going to look like. So when t is 0, r of t we showed was equal to the position vector r 0 0, or just r times I hat. And it's important that right from the beginning you remember that this expression is the same thing as r times cosine of omega t times I hat plus r times sine of omega t times j hat plus k times t times k hat. I guess k would probably be not the best thing to use here because you have a k hat here and a k here. So I think what I'll do is change this to just be, we'll use a. So for another possible value of t, we'll choose when t is equal to pi over 2 omega. And when that's the case, when we plug in here, we get that the position vector is in fact equal to the vector, well, when t is equal to pi over 2 omega, we get cosine of pi over 2 here, which is equal to 0. And so the first component will be 0. When t is equal to pi over 2 omega, we get sine of pi over 2, which is 1. So the second component is r. And the third component will be a times pi over 2 omega. That's the z coordinate, or the height at this point. So when t is pi over 2 omega, we're at a height right here, where the height here is a pi over 2 omega. And we see that it's not too hard to see that if you continue to connect in the dots here for any and all other values of t, you get a curve that looks like this. And similarly, if you continue to fill out this table, you will get the following sort of picture. Exactly like this. And what we're seeing here is that this is the shape of a helix. So this curve and this r of t, this parametric curve, is exactly the shape of a helix. I encourage you to do it for multiple different values of t, to see this for yourself. But what's really nice here, right, is that we can go through and actually see that a nice plot of this by using. I mean, you can do it using Python, but I think the easiest way for getting basic plots like this is to use various online tools. One of the best ones that I know of for plotting three-dimensional curves is called GeoGebra. So specifically it's GeoGebra 3D. So I'm going to take a little aside now to take a look at what this curve looks like in 3D. So sure enough, this here is what the curve looks like in 3 dimensions. If we change the value of omega, that frequency, it changes the number of, or the speed of revolutions. And if we change that R value, the helix becomes bigger or smaller, depending on what R is. And I use K here, but the K value is the same as the A value in the notes. If we change that, it changes the stretchiness of how stretched out this is. And obviously we can see that if K is 0, right, there's no change in the Z direction at all, and we just get a regular old circle instead of a helix. But for positive values of K, or A in the notes, this is changing how this helix is stretching versus, say, along the Z axis. So this is our first main example. And this is an example that we'll stick with for a while, especially as we move into the next topic, which is that of the first derivative of this vector valued function. And this first derivative of a vector valued function is also known as the velocity vector of the parametric curve. So recall that our position vector is on a curve, parametric curve, so it's a function of some parameter t. And recall how the derivative was defined in a single variable calculus course, your Calc 1 course. I'll put it in a bubble up here. So in 1D, let's put 1D. The derivative is defined as the limit as h goes to 0 of f of t plus h minus f of t divided by h. This is exactly what we call f prime at the point t if this limit exists. It's the first derivative of a scalar function of a scalar variable. I'll make that a little bit nicer. Let's make it a bubble. And think about what the most logical way of defining the derivative of a vector valued function now is of a scalar variable. We can almost directly extend this idea, and we're going to investigate for the helix and for some other examples as well exactly what the best way of extending this idea is. And the most direct extension of this idea we can see is just taking the limit for small values of change in the independent variable, the limit as h goes to 0 of the vector valued function at t plus h minus the vector valued function at t, and we divide that by h. and we call this the first derivative, or r prime, of this vector valued function. Another notation is, you can say it's dr dt. This is in fact the definition of what's called the velocity of a parametric curve. Which we denote by v of t. Now, it's fairly straightforward to go through and show that the coordinate form, this expression is independent of coordinates because it's just dealing with the vector itself. However, if you were to calculate this in coordinates, you have that v of t, or r prime of t. And let me go back to using the underline notation. We go through and try to find out what the coordinate form of this is. We end up seeing very, very quickly that this is the same thing as the limit as h goes to 0. And we do this subtraction and divide by h of the first component, the second component comes this difference quotient, and the third component becomes the difference quotient with z. So the coordinate form for the velocity just reduces to the individual normal derivative of each of the components. Or in terms of the ijk notation, is exactly x prime of t times I plus y prime of t times j plus z prime of t times k. So we'll take a look at what this looks like for the helix example. You can see right here we have the helix, and not only that, but on the helix itself we have this position vector, which is a black position vector right here at this point. And if I move the point C, which is in the parameter space, along the helix, this point C changes. And what I've also shown here is another point. This point is the position vector on the helix at C plus H. So in terms of our color coded here, the black vector is A of C, and the dark green vector W is A of C plus H. And this vector D right here is the difference vector between these 2 points. So it's exactly the numerator in that difference quotient. It's the A of C plus H minus A of C, or in terms of our notes, it's R of T plus H minus R of T. And you'll notice that that difference quotient, as H goes to 0, gets smaller and smaller and smaller and smaller. As we shrink H to 0, the vector difference between those 2 points gets very, very small and goes all the way to 0. However, if instead of just considering the difference R of T plus H minus R of T, we consider that difference quotient R of T plus H minus R of T over H divided by H, and that's represented by this purple vector right here. You'll see exactly what happens as H goes to 0. It's very cool. As H gets smaller and smaller and smaller and smaller, the way this purple vector is the vector b, you see that it directly approaches the tangent vector to the curve. It's a tangent vector, the magnitude of which we call the speed at a given point, and we can even travel all the way around this curve, and we see that as we travel along the curve, the tangent vector is changing. It depends on the position. So this is a very kind of cool diagram. And it shows exactly that this velocity vector is in fact the velocity vector of the curve, and it's generalizing for us the idea of the derivative of a single variable function, but now to the derivative of vector valued scalar or vector valued function of a scalar variable, which is very cool. The other thing that I want to note is that we can also, as long as this limit exists, we can define this limit in a number of different ways. Right? For instance, if you wanted to define or approximate the velocity vector at a point, you want to define it as the limit as h goes to 0 of r at t plus h over 2 minus r at t minus h over 2 divided by h, or the total distance between those 2 points. You can go right ahead and do that, and it turns out if you use this to approximate the tangent vector at a point, it's actually a better approximation at that point. But as long as the limit exists, this limit exists, it'll be the same thing as this limit right here. I'll show a picture of this right now so we can see that. So this right here is that same helix, but instead of using the difference between t and t plus h, this vector right here, this first green vector right here, is the position vector at t minus h over 2. And this position vector right here is the vector at t plus h over 2. And this vector right here is that difference quotient that I just wrote, r at t plus h over 2 minus r at t minus h over 2 over h. And you see exactly that as h gets smaller and smaller and smaller, this difference quotient directly approaches that same correct velocity vector, that same correct unique tangent vector. Right here, where we can do this at any point along the curve, and we'll get that tangent vector. This is definitely the correct way of defining the velocity. And the difference between these two definitions are just what it's called is the difference between a forward differencing formula and a central differencing formula, which numerically speaking, the central difference formula does have some advantages, and it's more accurate than the forward differencing or a backwards differencing formula, but I won't be getting into that. It's more of a topic for a numerical methods course. So, like I mentioned before, I want to write down that the speed at a point on the curve is defined as the magnitude or length of the vector v. And specifically, we're using what's called the concept of a norm, which is, there are actually multiple ways of defining a norm or length in mathematics, but we're using what's called the 2 norm for length, because this gives us very, very nice properties. So you'll remember that we can denote the norm of a vector, or the length of a vector will be denoted like this, with 2 lines around the vector. And if it's a vector in 3D, the 2 norm just says that this is the square root of the dot product of the vector with itself. Which, when we compute this out, reduces to, in Cartesian coordinates, v1 squared plus v2 squared plus v3 squared. And remember that I haven't written any functional dependence here, but v here in general on the curve is a function of t, which means that each one of these components is in general a function of t. Right? So this the speed is the magnitude of this vector v, in which case it's going to be the same thing as the magnitude of r prime of t. So this equation right here is the same thing as this equation right here, the second equation right here just denotes that explicit t dependence, the dependence on the parameter of the curve. But this is how we go through and calculate the speed function at any given point along the curve. And this is this, you can think of it as the instantaneous speed at a given point on the curve that's in the tangential direction, or along the vector v. Now remember that this formula, the magnitude formula, holds for any vector. For any vector, if we want the 2 norm length of that vector, we can apply this formula right here. It's a very important formula, actually, which we'll come to in a second. Suppose, instead of wanting the velocity vector, we just want a vector, we'll call it t hat, which we call the unit tangent vector to the curve r of t. It turns out this is going to be a very, very important quantity. So this is going to be a vector that's of unit length, or length 1, and always going to be tangent for any point on the curve r of t. Well, to compute this, all you have to do is remember what the velocity vector will show will always be, we can prove it's always tangent to the curve. And this tangent vector, this unit tangent vector, then can be constructed by directly taking what's called a unit vector in the direction of that vector v. So it's exactly defined by taking the vector v and dividing by the length of that vector v. So this is how we define the unit tangent vector. If we open up our plot of the helix example, we can directly see this. This orange vector that I've plotted right here is the unit tangent vector. And you see that as we move around the curve, and I'll kind of zoom in a little bit more so we can see this a little bit more. As we move along this curve, for more complicated functions, for the helix, the velocity is staying at the same value. This purple vector is the velocity vector, and it's not changing at all. But for more complicated curves, this length was definitely going to change. We'll see an example of that by the end of the lecture. But this unit vector, this tangent vector, always stays the same length regardless of the curve. But it's always points tangent to the curve, or tangentially to the curve. So that's this vector t that we just defined. So this is a very useful concept because it gives us an idea of just isolating the idea of tangent direction to a curve at any given point. And we'll see we can actually do this in multiple different directions. There's going to be 3 special directions associated with any curve, and we will get to that shortly, a little bit later on in the lecture. But before I do that, I want to talk about the next concept for curves, which is if we define the velocity using the derivative, we're going to end up defining what's called the arc length of a curve, or the length of a trajectory up to a time t, as follows. So for notation, this is a scalar function. We'll say s of t will denote arc length traced out by curve from some initial time, which very often could be 0, or not time, but parameter value, we'll say, because the parameter doesn't necessarily have to be time. To some final parameter value t. And the way that we define this is as following. We know that s of t is equal to the definite integral from 0 to whatever that value is of 1 ds and if we convert this integral into the parameter value, this is the same thing as the parameter from the integral from t naught to t of s prime of t dt, where s prime of t is exactly the rate of change of arc length along the curve at any given point t. So the idea is that if we can evaluate this integral, we can compute the arc length. But remember, this is the rate of change of arc length with respect to the parameter value t. It's exactly the same thing as the integral of the magnitude of dr dt, or the same thing as the integral from t naught to t of the magnitude of the velocity vector as a function of t. Remember, this is a function of t. Or in long form, if we actually plug in this magnitude, the formula that we have for the arc length is the integral from t naught to t of x prime squared plus y prime squared plus z prime squared dt. So this is, if you have to figure out the arc length along a curve, this would be the formula that you would have to use. You have to figure out what this function is a function of t, and the magnitude of the velocity vector. Then you have to integrate that magnitude function, and it could very well be very complicated. However, if we go through, and it's important to note here that we've used that the tangential speed, or the rate of change of arc length along the curve with respect to the parameter t, is exactly the velocity vector at t. And this will also be very, very important in the future. Let's stick with the helix example. Say on the helix that we described before, we want to figure out the arc length from t naught to t. Now recall that the helix equation is parameterized like this. So the velocity vector for the helix is the first derivative of this expression right here, which in terms of our vector notation is going to be negative omega r cosine of omega t, and sine of omega t is the first derivative of that first component. Omega r cosine of omega t, and the derivative of this expression of a times t is just a. And so the magnitude of the velocity vector for the helix as a function of t is going to be negative omega r sine of omega t squared plus omega r cosine of omega t squared plus a squared all raised to the power 1/2. And we see very quickly that this is going to simplify. We can factor out omega r squared, and we get sine squared plus cosine squared, which is 1. So this just becomes omega r squared plus a squared, the 1/2, or the square root of omega r squared plus a squared. And so the for the helix, we actually just proved exactly what we noticed when we plotted out the velocity vector in that plot, which is that the magnitude of the velocity vector is constant for the helix. It does not depend on the parameter t. Okay, this is a very special thing. It's not true in general for general parametric curves. In general, that velocity vector is changing. It's an actual function of t, but this is one of the reasons why the helix is a very special curve. There's a number of different other reasons as well, but this should serve as a good example of calculating the velocity vector, so the magnitude of the velocity vector. And now to calculate arc length along the curve, which is the point of this example, we use the fact that arc length from t naught to t will be the integral of the velocity function, which in general is a complicated function of t. So this integral isn't always that easy to evaluate. But in this case, it doesn't depend on t at all. So it's constant, and it comes out of the integral. And we have a very nice expression for the arc length function as a function of t is just the function square root of omega r squared plus a squared multiplied by t minus t naught. So in general, this would be how you would compute arc length between two parameter values on the helix. You have to put in your value of a, so the rate of growth along the z-axis, your radius of the helix, and your value of omega, which is the frequency that it's spinning around. Well, we can clearly see that this formula is giving us a nice formula that we can use. Now, in general, I want to emphasize again that it's not always that easy to do this integral. These integrals can be very complicated because the magnitude of v of t could be a very complicated function of t. But the helix is a very, very nice example. It doesn't really require us to do any sorts of integration at all. So the last part of this section is that we want to actually use this idea of arc length now and do what's called reparameterize. So I've been intentionally vague about the parameter t. Right, this very often in physics could be time. So a time scale parameter t could be time. If you're studying, say, the trajectory of particles in a particle accelerator, or t, you could parameterize, say, by theta. Right, in some ways, for the helix, we can think of t as an angle theta going around from the x-axis, going around the z-axis, measured from the x-axis. But it turns out that it's actually really important to consider how we're parameterizing a given parametric curve. And not only that, but there's in some senses, for certain reasons, a very preferred reason for us to do what's called parameterized by arc length. And the main idea here is due to geometric, the geometric invariance. Right, the arc length itself, in some sense, gives us a very, very nice uniform parameterization that we can apply always, and we can always switch to an arc length parameterization. And that's directly based on what we showed as we were going through in defining arc length, which is that the rate of change of arc length with respect to any parameter t is exactly the velocity vector at t. So you'll recall that we defined the velocity vector as the derivative of the position vector with respect to the parameter t. This parameter could be time, it could be an angle, it could be a number of different things, as long as it's a scalar parameter. And well, you'll remember from the chain rule from Calculus 1, which really, it's not too hard to extend the chain rule. Right here you have that. If you have, say, that R, the position vector, depends on, say, our three components, x, y, and z, and each of these components depend on t individually, but say we want to reparameterize these by arc length, then you know that by the chain rule here, dr dt is going to be the same thing as dr ds times ds dt. And this is from the basic chain rule just applied to this chain right here. You don't even need to think of r depending on x, y, and z right now if you don't want to. It's relatively straightforward to see this, hopefully. So from the basic single variable chain rule, we have this result right here. And now remember, ds dt is nothing but that magnitude of the velocity vector. So this is the same thing as dr ds times the magnitude of the velocity vector. And actually what this tells us is the following. If we divide both sides by the magnitude of the velocity vector, we have that the rate of change of position with respect to arc length s is exactly the same thing as the velocity vector divided by the magnitude of the velocity vector. And you'll remember that this is exactly how we defined the unit tangent vector. And we'll put a hat on it to note that it's a unit vector. So this is a very useful formula, and we'll see why in a little bit when we start talking about the acceleration. Mainly, the use of this formula is going to come in what I was talking about before, how we can decompose any vector into very special directions on every curve. And these special directions are called the tangent direction, which we've already defined, the normal direction, and the binormal direction. So in 3D we can always form this decomposition and use it to describe what's called a frame tangent to the curve, along the curve in three-dimensional space. So we'll get into this in a little bit later on in the lecture. So the next section that we're going to talk about in today's lecture is going to be how to take the derivative of the dot product and the cross product. These are some useful identities that will be useful to us moving forward in terms of simplifying calculations when we have the derivative of a vector valued function of a scalar variable. So remember that if we have two vector valued functions, a of t, where this is a1 I plus a2 j plus a3 k, and same thing for b of t, b1i plus b2j plus b3k. We call that the dot product. Can be computed in a number of different ways, but in terms of this, our Euclidean coordinates, the dot product is going to be the dot product of this vector dot product with this vector. And using our normal laws of the dot product, obeys the normal laws of algebra. In which case we can expand this out, and it'll be a1 I dot I plus a2 j dot j plus a3 k dot k. And we also do have a number of other combinations. We have a1 b1 I dot j, a1 b3 I dot k, a2 b1 j dot I. Oops, and this should be a1 b2 plus a2 b3 k or j dot k plus a3 b1 k dot I plus a3 b2 k dot j. And this would be the general way of taking the dot product if our basis were not a Cartesian basis. But this simplifies a lot in Cartesian coordinates, because we know that, for instance, I dot j is the dot product of the vector 1, 0, 0 with the vector 0, 1, 0, which is just equal to 0. So each one of these, I dot j, I dot k, j dot I, j dot k, k dot I, each one of these is just equal to 0. While each one of these values, I dot I, j dot j, and k dot k is in fact equal to 1. Oh, and we need to have, this should be a1 times b1, a2 times b2, and a3 times b3. So in general, this is the correct way of taking the dot product in an arbitrary basis, but with respect to a Cartesian basis, a of t dot b of t is just equal to a1 times b1 plus a2 times b2 plus a3 times b3. And this should give you a hint of where we're going here when we take the derivative of this this general dot product. This means that the derivative of the dot product of two parametric functions is going to be the same thing as the derivative of the sum of the multiplication of the components, or the component functions. And we know from calculus 1 that this is the same thing as the sum of the derivative of each one of these products, which we calculate using the product rule. So it's a1 prime times b1 plus a1 times b1 prime plus a2 prime b2 plus a2 times b2 prime. And then lastly, let's see if we can fit this here. One nice line. It'll be a3 prime times b3 plus a3 times b3 prime. And if we regroup, that means that we've shown that the derivative of the dot product of two parametric functions, or two vector valued functions of a scalar variable, satisfy the normal product rule. So this is going to be the same thing as the derivative of A dot product with B plus A dot product with B prime. Now, in general, we do have to be careful to verify any rules from calculus 1 that we're going to try to apply to vector functions, because depending on the operation, these could be the rules could extend a little bit more generally than they do in Calc 1. They could be a little bit more complicated. But a good exercise would be to go through and show that we also have a similar simplification for the cross product. Namely that the product rule, if you take the vector function a of t, and you take the cross product, the vector cross product with the vector function b of t, this will be the same as the derivative of a of t cross product with b of t plus a of t cross product with the derivative of b of t. And we'll see examples later on in the course for of times when the derivative laws don't extend as nicely. But what's really nice is that both for dot product and cross product of a vector valued function of a scalar variable, the normal product rule holds. And I recommend going through and showing this. It'd be a good exercise to show this for the cross product. But because of that, we can actually go through and directly prove something now that's going to be of fundamental importance going forward. So if we consider that unit tangent vector from before, you remember that the unit tangent vector, the length of it is 1 because it's a unit vector. And directly from this expression, this should be squared right here. Directly from this expression right here, if we take the derivative of this expression, so we take the t derivative of both sides of this expression, this is going to give us the following. Well, on the left-hand side, we can apply the product rule that we just proved. And the derivative of 1 is 0. So we've just shown that 2 times the dot product of t hat with t hat prime is equal to 0, or the unit tangent vector dotted with this new vector t hat prime is equal to 0. So we've just kind of stumbled upon this new vector t hat prime, or the rate of change of the unit tangent vector with respect to the parameter t, and we've shown that it's actually perpendicular to the tangent vector itself. So t is perpendicular to its derivative, t hat prime. And this is very, very special in some sense, because this actually gives us the way forward for constructing that frame that I talked about before, the orthogonal frame. We define the following. Now, this vector t hat prime is not necessarily a unit vector, and in general it's not a unit vector. So what we do is we define the vector n hat as the vector pointing in the direction of t hat prime, the unit vector pointing in that direction. So it's the vector t hat prime divided by the magnitude of t hat prime. And remember that these are both functions of t, so if you want to include that, that'd be a good thing to include. Oftentimes we won't include that because we'll leave it as assumed, but we want to be careful when we're talking about vector functions that we denote that they depend on some independent variable. So this vector is called the unit normal vector to the curve r of t at a given point. And it's important to remember that it's perpendicular to the original tangent vector. So what's important about this is that it singles out a special perpendicular vector called the unit normal, or sometimes called the principal normal vector to the curve r of t at a given point. And just to kind of go back to our example, let's take a look at our example and we'll show what this looks like. So on this plot here, I've shown a plot of the tangent vector, so that unit tangent vector which is in orange, this vector f right here, alongside the unit normal vector. And sure enough, you can see that as we move along the curve, that vector is always staying perpendicular to the unit tangent vector. And you can kind of get an idea of why we call it the unit normal vector, because it's always pointing normal to the curve itself, or normal to the tangent vector of the curve itself.